Everyone is able to see my
Yes,
screen?
yes, we can see it. Good to go.
Okay. So first, thank you for organizing a nice conference, the virtual meeting. And I am now a postdoctoral research associate at the University of Massachusetts Lowell. And today I will talk about the distinguishing between flaring and non-flaring activations. So this distinction between flaring and non-flaring activations is important because of the base weather from prediction point of view. So what is base weather and how it works? So the coronal mass ejection and the solar flare, these are the two biggest explosions in the solar system. And these explosions directly hit the Earth's magnetosphere and creates the geomagnetic disturbances. And because of these disturbances, many of our satellites and power grids destroyed totally, and specifically in the polar region. So it is important to predict the phase weather earlier such that we can protect our instruments. So now question is how we can predict this kind of phase weather disturbances, because AB flare and CME is not the earth directed. So only few flare and CME, which is the coronal mass ejection, is earth directed, and they are actually responsible for the geomagnetic disturbances. So what is solar flare? So solar flare is basically a sudden, intense, and rapid variation in the brightness in the solar atmosphere. And when a solar flare occurs, the magnetic energy that has built up in the solar atmosphere is suddenly released, and radiation is emitted because of this release virtually across the all electromagnetic spectrum from radio to long. And also some emission was there in X-ray and gamma ray. And now we can distinguish the solar flare in terms of the peak X-ray flux. So if you see here that there are the classification of the flares, class A, B, C, M, and X, and these are the corresponding energy. And so you see that mostly the X class and M class flares are high energy, and these class flares have significant impact on the behavior of base climate. And if you see the plot in the right hand side, which is the plot of solar irradiance, which is along the y-axis, and the x-axis is the time, see that how in the flare phase or impulsive phase, the solar irradiance increases. And M class and X class flares are highly impactful. So we focus here to distinguish or to predict these X and M class flares from the others. So there are different ways to predict the solar storms. One is empirical or statistical way, another is MHD simulation, and third is the machine learning. So here our approach is the machine learning. And there are also recently few papers on this kind of flare semi prediction by Bob nowadays and Liu et al. But our aim is the machine learning. So what we know earlier that in the sun, there are active regions, which is basically the black spot on the solar surface. And when this number of black spots increases, then there is large number of flare and coronal mass ejection. So it is believed that there is a direct link between these active regions on the solar surface, which is basically the black spots, with the production of flare and coronal mass ejection. So now I will talk something about the machine learning part. So machine learning is basically a branch of artificial intelligence which provides a computer the ability to learn automatically and improve from past experience without being explicitly programmed. So in machine learning literature, there are actually two types of learning. One is supervised learning and another is unsupervised learning. And all you know that in the machine learning approach, what one have to do, first one have to train the computer. It is basically you have to teach the computer such that computer can take his own decision. It is in simply, it is similar like a children. So when a children born or comes into the art for the first time, he is a complete black box. Later, what happens? His teachers and parents teach him by showing defiant objects like, okay, it's mango or it's banana. And by seeing after that teaching, child can take his own decision. That means one have to supervise the children such that children is able to take his own decision, and this is supervised learning. And same procedure we will follow to teach a computer. In computer also, for the computer in machine learning, there is also supervised learning. So in supervised learning, what we do, we will give the computer the labels. Okay, suppose I want to distinguish the flaring and non-flaring region. So let label the flaring regions as red and non-flaring regions as blue. So by providing the labels and some past data, we will be we will teach the computer, and after that we will provide new data to the computer, and computer will take his own decision. And that's the method of supervised learning, means labels are given. However, it is not possible for parents also to teach everything to children. However, child will learn by interacting with environment. Means if you ask a children, okay, this is two cities, one is Boston and another is Singapore. And if you ask the children that, okay, let me tell whether Boston is in United States or Singapore is in United States, he will clearly distinguish these children even without teaching him. He will classify the Boston into the United States because he know that distance, that distance of United States where it's located is near to Boston. So just by interacting with environment, even if you without teaching, he will be able to classify. And that's the unsupervised learning. So in unsupervised learning, actually, basically labels are not given. So this is the basic machine learning pipeline. So first one have to create the data sets, and then the data preparation part, which is involved data processing, and then the feature extraction, and finally the feature scaling and selection. And after this data preparation part, when our data set is ready, we will train the computer by the machine learning algorithms. And then finally, we will evaluate our model with the new testing data set. And after that, we will deploy this for the prediction purpose. And this is the basic standard pipeline of supervised machine learning or unsupervised. Okay, so now I will describe the flow of supervised machine learning. So first part, what I told you earlier, the preparation of the data, which is the most important part, and then divide the data set into training and testing data set. Let's say 70% for training and 30% for testing. And this 70% data set we will use for the purpose of teaching the computer. So train the computer based on the training data set. So in the training data set, you will have all the parameters as well as the target output, because we will teach the computer based on past known data set. And from this training data set, computer will learn using different machine learning algorithms. Then provide the testing data, which will be without target level load output to computer, and computer will predict the target level load output automatically using the previous learning experience. And finally, compare computer predicted target output with the original target level load output. And you will get the accuracy of your model. And if accuracy of your model is good, your model is then ready for prediction. So here is the data, our data set, which we used for the purpose of training. And we extracted the data sets from the SDO, Solar Dynamical Observatory, HMI vector magnetogram, which is the total unsigned current helicity, total magnitude of Lorentz force, photospheric magnetic free energy density, unsigned vertical current helicity, total unsigned flux. So these are different magnetic parameters which we extracted from this vector magnetogram. And now we will use this, and in previous data set, we know that which activation is produced flare or which activation don't produce flare. And these are the magnetic parameters. So we now have all the parameters, and we also have the target level. So, and based on this past data set, we will train the computers. So now this is just some analysis of some activation magnetic properties, and let's see that how it behaves in the flaring and non-flaring activations before the training, obviously. So here you see that in the flaring activation, you see that unsigned magnetic flux, which is along the x-axis, US flux, and this is the time. And these are the other parameters, the total unsigned vertical current, total unsigned magnetic helicity, and total photospheric magnetic free energy density. And how it evolves with time. And you see these blue dot dash lines, these are actually the time when the flare takes place. So it becomes clear that one activation produces lots of flare in its period when these activations are present in the disk, solar disk. And here you see that in the non-flaring activation, how it behaves. So there are evolutions in both flaring and non-flaring. So in the right-hand side, you see there are no flares. However, if you compare the magnitudes, you see here in the non-flying, it is 10 to the power 21. However, it is, in case of flying, it is 10 to the power 22. So all selected four magnetic quantities in flaring activations has much higher value compared to the non-flaring. So this is first conclusion from here. And second conclusion is what? That when flare touch in a activation, it keeps on flaring. Third, every activation is unique. So we have to find some unique clue which can distinguish the flaring activation from the non-flaring one. And more disturbing fact, what I want to focus, that flaring activation is always in flaring state. So if you see that in this flaring activation, flare occurs at 5th of September first. However, the flux value is also higher in 3rd September and before. But flare did not take place. It only occurs at 5th, and that's the problem and of the flare prediction. So it's an extremely challenging task. So here we don't focus on to the prediction of FG is flare. However, for this study we focus on the basically the distinction between this flaring and non-flaring region. So in what we use for the preparation of our data set, so this is the T is the time of solar flare. So we go back some hour, let's say 24 hour or 48 hour, means which is when we want to predict the flare 48 hour before or 24 hour before. And then previous all the theoretical studies predict that the time evolution of magnetic parameters are actually responsible for flare. So what we did, we use a time span of S, and during this time span, we calculate the evolution of all magnetic parameters. And based on this evolution parameters, we train the computer to predict the flare L time later or 24 hour or 48 hour later. So now we have all the time evolution data of the magnetic parameters, but we have to find out a way by which we can train the computer, because for computer training, we have to give them some summary statistics. So what we did here, we present our multiple here time series using 8 summary statistics: mean, standard deviation, Q-ness, and kurtosis. And again, next for all these mean, standard deviation, Q-ness, and kurtosis of the first derivative of the time series. So we actually capture the statistical information of the time series using these 8 statistical parameters. However, again, we agree that this is not the best option, but this is the most similar option. And what we did this, because you know already from the theory that flux cancellation along the polarity inversion line is the mechanism which triggers the solar flare and CME. That's the time series information is necessary for the training purpose. And that's why we take this approach. And at this moment, we don't know any way to use this full time series information. Maybe later some other information, like one can do the wavelet analysis or something to give the full information. But for this study, we use the most simpler approach. And there are different classifiers we use, but in machine learning, what we have to do, first we have to use a simple classifier, which will act as a baseline classifier. And if baseline classifier gives you the best result, then it is not good to go for some complex classifier like neural network, support vector machine. And we choose the logistic regression as our baseline classifier because it is easy to implement, easy to interpret, efficient, and does not require high computation power. And in logistic regression method actually estimates the probability of an event occurrence by fitting the data to a logistic function. And this is the equation used for the model, logistic regression model. And this x1, x2, xn is the variables, and p by 1 minus p is known as the odd ratio. And if this odd ratio is positive, then the probability of event occurrence is more than 50%. And so this algorithm, this logistic regression algorithm actually separates the classes by constructing a linear decision boundary between them. So here what we did, we used this baseline classifier model to distinguish these two. So after that, after deployment of model, we will get some result. So we have to measure the performance. So there are different ways to measure the performance. Most best way is the confusion matrix, which is basically two positive are the cases when the actual data points are true, means positive or flaring, and the predicted is also true. This is false positive, means actual class of data points are negative. However, our model prediction is true. Then this is the false positive. And this is false negative. So actually, the data point is negative, but actually data point is positive, but our model predicts negative. So this is the false negative. And again, actually the data point is negative, but our model predicts also negative. So this is true negative. And these four quantities will construct a matrix, and this is known as the confusion matrix. So here I again describe the true negative are the cases, and the actual class of data points was negative and the predicted is also negative. False positive are the cases when the actual class of data points was negative, but predicted is also positive, then it is false positive and false negative. And accuracy in a classification problem is the number of correct predictions made by the model over all kinds of prediction made. So accuracy is a good measure when the data set is balanced. There are some another measures, so it is precision, which is basically TP, which is true positive by TP plus FP. And it tells us how confident we can be that an instance predicted to have the positive target level actually has the positive target level. Is equal and the specificity. Equal tells us how confident we can be that all the intents with the positive target level have been found by the model. So now problem is that in most cases the dataset is imbalanced. That means there are lots of activation, only few is flying. Like there are 10,000 data points, but only 50 or 100 is flying. Or let's say we want to predict the cancer data set, means few people have cancer, whereas most of the people have non-cancer. So data set is highly imbalanced. So in imbalanced data set case, what will happen that if the model predicts, like a from a cancer data set, if model predicts all the people has a no cancer, then also your accuracy will be very high. Or in the case of flying data set, if model predicts, okay, all activision is non-flying, then also accuracy will be more than 80%. So accuracy is not a good measure. This accuracy is equal, these are not good measure in case of data set when data sets are imbalanced. So many performance are by the class imbalance. So we have to find out some way which will tackle this imbalance issue. So there are many performance measures like Gilbert skill code, Heidke skill code. They are used in this case. And another more important is the two skill statistics. And two skill statistic is more important parameter in case when the dataset is imbalanced, because the Heidke skill code or Gilbert skill still shows some dependence on class imbalance. However, this two skill statistics is imbalance of independent on class imbalance, and it ranges from -1 to +1. Perfect prediction scores +1, and wrong prediction scores -1. So it is the most meaningful measure when the data set is imbalanced. And there is also average class accuracy. These are another measure. However, mostly important measure is the two skill statistics. So now what we did, we created different data sets. Like loop 24 pan 12 means we go back 24 hours and then we use 12-hour time evolution. In second case, loop 24 pan 24, again span is the time duration for the calculation of our time evolution. And again it is 24-hour back. And we also created few data sets where we used only 12-hour time evolution, but we want to predict only 12-hour before and also 48-hour before. And what we find that when we use the time evolution, we are able to get very good two skill statistics, which is of the order of 0.87 almost. Obviously, when we want to predict 12-hour before, we got very good 0.92, but also 48-hour before, we get very good. So the method of training the computer is good. That's why we are able to get so good result. And even if we have almost total 16 magnetic or 20 magnetic parameter, however, if we consider only the top 5, then also we are able to get almost similar accuracy of two skill statistics. And next we want to focus on the best parameter, that which parameters are best in terms of distinguishing capability. So what we find that the unsigned flux, and these are the all magnetic parameters, and these are from two different methods. In one case it's from logistic regression and another is from support vector machine. And we find that our baseline classifier works well, and the other methods like SVM, deep learning also gives almost similar accuracy. And if we compare these, just we find that unsigned flux and total unsigned magnetic helicity have the best distinguishing capability. So in summary, what we did, we have performed a comparison study between adaptive and non-reactive activisions in terms of the time evolution of the photospheric magnetic parameters. Second, as it is not possible to analyze all flaring events manually because there are large amount of solar data, so it is simply not possible. We use machine learning algorithm to distinguish adaptive activism from the non-adaptive one. And specifically, in this study, we use the time evolution of parameters to train the computer, which no previous study did. And so it is possible to distinguish flying activism from the non-flying one with good accuracy. And we determine the common critical magnetic parameter that clearly distinguishes adaptive activism from the non-reactive one. And we find that time evolution of total unsigned magnetic helicity and total unsigned magnetic flux have a very high distinguishing capability. So in summary, our model can do, it can distinguish from the flaring one from the non-flaring with very good accuracy. But again, our model actually fails to predict solar flare at a particular time. Means prediction of time is another important task. So our model is not able to do that because what I told you earlier, that once the activation is in the flaring, it's always in the flaring state. So that is our next aim. We are in future we are expecting to improve our model such that we can also predict solar flare or how many flares will take place in a activation, that we can predict clearly. So anyway, thank you.